Welcome to Exam Menu Video 3. Today we are talking about the Hardy-Weinberg equilibrium. Please pause and look over these review and new terms if need be. Now, what is Hardy-Weinberg equilibrium? The Hardy-Weinberg law states that the allele and genotype frequencies after one generation of random mating will arrive and remain at equilibrium frequencies if all assumptions are met. These assumptions are that the population is indefinitely large, that random mating occurs, that there is no selection, that there is no migration, and that there are no genetic mutations. The genotypic frequencies in equilibrium are represented by this equation. The variables in this equation, P and Q, represent the allele frequencies of the dominant and recessive alleles respectively. Let's see this in practice. Let's say that we have a population of ladybugs in which there are 49 homozygous dominant genotypes producing a red body phenotype, there are 42 heterozygous genotypes producing a yellow body phenotype, and there are 9 homozygous recessive genotypes producing a green body type, giving us a total of 100 ladybugs in our population. Let's confirm that our population is in Hardy-Weinberg equilibrium. To determine the frequency of each genotype, we divide the number of individuals with that genotype by the total number of individuals in the population. We then get a homozygous dominant frequency of 0.49, a heterozygote frequency of 0.42, and a homozygous recessive frequency of 0.09. To find the allele frequencies, we need to take the square root of each homozygous genotypic frequency, which gives us a dominant allele frequency of 0.7 and a recessive allele frequency of 0.3. Both of these frequency sets add up to 1, which is consistent with Hardy-Weinberg requirements, confirming that our population is in Hardy-Weinberg equilibrium. But what happens if one of the assumptions are violated? For example, selection. There are 3 different types of selection that can affect a population. The first is disruptive selection, in which both homozygotes hold an advantage, which cause those frequencies to increase while the heterozygote frequency decreases. In the case of our ladybugs, that would be like if the red ladybugs survive better because of their warning color, and the green ladybugs survive better because of their camouflage. The second is stabilizing selection, which favors the heterozygote, decreasing the frequencies of the homozygote. This would happen if the yellow ladybugs were able to camouflage better than the green ones, and the red ladybugs did not ward off predators. The final one is directional selection, which favors only one of the homozygotes, causing the frequencies to shift over time towards the favorable genotype. For our ladybugs, this would happen if neither the yellow nor the green ladybug were able to blend in, and only the red ladybug was able to evade predators. Let's further explore how directional selection violates the Hardy-Weinberg equilibrium. As you can see in this table, we already know our initial frequencies from our previous calculations. The fitness of each genotype is given, and as we can see, the homozygous dominant genotype has the highest fitness, so selection will move towards that direction. To calculate the unadjusted survivors, we calculate those of each genotype by multiplying its frequency portion of the equilibrium equation by its fitness. This gives the red ladybug a value of 0.49, the yellow ladybug a value of 0.336, and the green ladybug a value of 0.054. To find the new genotypic frequencies, we first need to find the average fitness by adding the unadjusted survival values together to get a value of 0.8314. Then, to calculate the new genotypic frequencies, we must divide the unadjusted survivor value by the average fitness. The new genotypic frequencies are 0.5894 for the homozygous dominant genotype, 0.4041 for the heterozygous genotype, and 0.0650 for the homozygous recessive genotype. As you can see, our population has come out of Hardy-Weinberg equilibrium because the genotypic frequencies have changed. This shift will continue until the entire population is homozygous dominant. That is the end of this video. Stay tuned for another in 2 weeks.